Hi everyone, welcome back to another geometry video. In this video, we'll be going over apothems. So what is an apothem? The apothem of a geometrical figure is a line connecting the center of the figure to one of the sides. So a note is that the figure has to be a regular figure. So suppose we have this regular hexagon, and we're given this is the center, point T. So if we connect this line all the way to the bottom and say the point of intersection to the line as A, one thing about an apothem is that it is the perpendicular bisector of the side. So both of these sides are congruent to each other. So over here, TA, segment TA is the apothem. And let's just say X and U. XA is congruent to AU. So how can we use an apothem? So in geometry, the primary use of an apothem is to find the area of any two-dimensional figure. And we're given either the length of one side or the area of or the length of an apothem. The equation to find the area of a figure is A is equal to 1 by 2 AP or AP over 2, which basically means area is equal to 1 by 2 apothem times perimeter. So how do we find the apothem or the perimeter of a figure when we're given either only the apothem or only the perimeter? So suppose let's take the hexagon from the previous figure, but instead let's give them values. So suppose we're only given the side length of this hexagon as 10 centimeters, and we're not given the apothem. So the first thing we would do is construct a triangle by connecting the center of this figure to one of the sides. One of the vertices. So now that we've connected it, another thing we know is that since it's a regular hexagon, all sides are congruent. So let me reconstruct the figure over here. So since we know that, and we also know that these two segments made are congruent, we can say this is 5 centimeters. So we could construct a triangle. So the next thing we know is that over here we form a 360-degree angle. And since there are 6 sides to this figure, if we divided 360 over 6, we would get 60 degrees, which basically gives us this whole angle. Since if you look at it in a figure, 1, 2, 3, 4, 5, and 6 of these angles are made. So that basically means that the measure of the larger angle is 60, or if I were to clean it up, in that figure, what I was saying is that this angle over here is 60 degrees. However, if we would want to use trigonometric ratios such as sine, cosine, or tangent, we would first need to find the measure of this angle, not the whole, but this. And since we know that this is a perpendicular bisector, we also know that this is an angle bisector, or this line over here made is an angle bisector. Thus, if we were to construct a line and find this angle, we could say that it's 30 degrees. And since we know that this is 5, we could do tan or tangent 30 is equal to this angle measure, this line measure over here, which is 5, over this missing side, which we could call B. So all we need to do is replace these two and get B is equal to 5 over tangent 30, or the missing length is 5 over tangent 30, or the apothem is 5 over tangent 30. So 5 over tangent 30 is 8.66, or approximately 8.7. So the length of B is approximately 8.7 centimeters. So next we could find the perimeter. So 10 into 6 gives us 60, and 60 times 8.7 over 2 is approximately 259.8 centimeters squared, which is the area of this figure. Of this hexagon. So now that we know how to solve for the area of a figure, let's do a few more problems. Or that is an equilateral regular figure. So suppose we're given this equilateral triangle. However, in this figure, we're only given the apothem as 4 centimeters. So to solve for the area, all we need to do is first construct a triangle connecting the center to the vertex, which basically means this is 4, and we need to find this measure. So similarly how we did other problems, we can find this angle measure by first doing 360 divided by 3, which gives us 120. Since it's a triangle, 3 sides, so 360 divided by 3 gives us 120, and then we could divide that by 2, which is 60 degrees, to get this measure. And now that we have that, if you see closely, 90 degrees here and 30 degrees over here. So if you flip that around, you inherently have a 30, 60, 90 special right triangle where the base measure is 4. And one rule we know about a 30, 60 triangle is that if this is L, then this is 2L, and this is L root 3. So all we need to do is do 2 and a 4, which is 8. So the hypotenuse of this triangle is 8. And 4 root 3, which gives us this length. So now that we have this measure, we could do 4 root 3 times 2, which is equal to 8 root 3. And then we could do 8 root 3 times 3 to get 24 root 3. And now that we have 24 root 3, we could do 24 root 3 times 4 over 2, which is the area of this equilateral triangle. So all I did there was 4 root 3 times 2, 8 root 3 times 3, 24 root 3 times 4, and then all of this over 2, which is approximately 83.14. So let's solve one last problem. We're given a hexagon with a side length of 8 inches. So first we would connect the center of it to the vertex, and then 8 by 2 gives us 4, and then since it has 6 sides, 360 over 6 will give us 60, over 2 will give us 30. So this is 30 degrees. So now that we know that that's 30 degrees, we could do 10 to 30, or we know that it's also a right triangle or a special right triangle formed here. So since this is 4, this is the shorter side, so this would be 4 root 3 over here. And then you could do 4 root 3 times 8 into 6, so 4 root 3 into 48 to get 332.55, and if you divide that by 2, you get approximately 166.3, which is the area of this figure. And since this is inches squared, and that's the final area of this regular hexagon. So that's all I have for this video. I hope this video helped you with apothems, and thank you for watching, and I hope I see you next time. Bye!